Hi everyone, our project is Diffusion. We want to train and compare diffusion models with different techniques. To start, diffusion models are a class of generative models that work by adding noise to images and then learning to reverse that process. These models are behind many modern image generators, but the downside is that they are slow and compute hungry. In this project, our goal is to compare several diffusion variants and see how each technique trades off image quality versus efficiency. DDPM is our baseline method. It gives good image quality, but it needs a lot of tiny steps, so generating each image is slow. DDIM keeps the same trained model, but it uses a smarter way to step through time so we can take larger steps. This means fewer denoising steps and faster sampling, usually with similar visual quality. Beyond basic diffusion, we use a VAE to run diffusion in a compressed latent space for efficiency, CFG to mix conditional and unconditional predictions so samples better match the target class, and a cosine noise schedule plus learned variance to tweak how noise is added for more stable, high-quality generation. All of this is implemented with a UNet, which is a standard encoder-decoder CNN. This slide shows our latent DDPM plus CFG pipeline. We train by encoding a clean image with a frozen VAE, adding noise at a random time step, and having the UNet predict that noise in latent space. At inference, we start from random latent noise, run the UNet twice per step, and combine the predictions with guidance to steer toward the target class. Then decode the final clean latent with the VAE to get the image. We train and evaluate on image 100, using about half of the training split for learning and full validation split as real data. We report FID and IS to measure the performance. This table summarizes our baseline and extensions. Row 1 is the baseline DDPM with a linear schedule, fixed variance, and 1,000 steps. Row 2 to 3 replace DDPM with DDIM to test faster sampling. Rows 4 to 6 add a CFG on top of DDIM. And rows 7 to 10 are ablation variants with learned variance and cosine schedules. Results show that DDIM sampling slightly improves FID while using far fewer steps, but the largest gains come from CFG, which pushes FID down and IS up, with DDIM plus CFG giving a strong quality speed trade-off. In contrast, learned variance and cosine schedules are unstable. After that, we tested the effect of UNet and VAE. We have three configs from small to big. Results show that scaling up the pixel space UNet steadily improves FID and IS, while latent diffusion with a frozen heavily compressed VAE remains limited despite competitive IS, mainly due to VAE bottlenecks and limited latent training. Here are some samples from our diffusion model. They generally capture overall color and rough object shape, but many are still blurry or distorted with artifacts. Our main findings are that CFG provides the largest quality boost. DDIM gives a modest but useful speed quality trade-off, and bigger UNets consistently improve results, while learned variance, cosine schedules, and latent diffusion with a frozen heavily compressed VAE all hurt performance in our setting. Going forward, we'd like to use the full dataset and train longer. We also want to systematically explore better schedules, variance types, and more advanced guidance schemes. And this is our reference for our project. Thank you for watching.